lecture or their work, give lectures of interest to general audience. At least we have one on I'm part of the committee as well as the scenario. That's the reason why I announced this. Different committee members introduce either the speaker or the person, the advisor who is going to introduce the speaker. And I actually don't have to introduce myself. I'm sorry that I apologize to the speaker that we have such a distinguished audience.
Oh, yeah, that's good.
And may I introduce Dominic? Introduce Bryce.
Thanks,
Dominic,
John.
and as you all know, Dominic is Bryce.
So it's a pleasure to introduce Bryce Gadway here as our speaker. Bryce came to Stony Brook in 2007 from Colgate, just having won ABS after a war. And I think he floated around the lab already around this time, but joined formally Brook in 2008 in summer. And I mean, as almost everybody knows, Bryce is a real engine, a real steam engine. And so, yes, over the past 3.5 years, 4 years, has done incredible things in my lab, the interface between atomic physics and quantum optics and condensed matter. I just mentioned that you are first author on 5 publications, and 3 of them hopefully through URLs and 1 Nature Physics. So that's certainly been very nice time. And we're going to graduate soon, unfortunately for us. Just today, Bryce told me that he got the NRC fellowship for postdoc at Chira. And that's going to be in the group of Junier and David Jane. And so the plan is that you'll start this sometime in November. It's a Freudian year, September. And so I wish you all good luck with that. But for now, I'm very thankful what we did over here so far and are still doing. And so it's a pleasure to introduce you, and we're looking forward to your talk.
Okay, thanks. Okay. So today I'll be talking about a recent experiment we performed which looked at matter wave diffraction used to basically detect structure in an ultra-cold quantum gas. And just listing some funding which makes the research in the lab possible. And quick outline, I'll give a brief motivation for the physics that we do in our lab, some background onto matter waves and Bose-Einstein condensation. I'll describe the experimental setup that we use, and then I'll talk specifically about an experiment looking at matter wave crystallography, and then I'll have some concluding remarks. So what we do in the lab can best be characterized as quantum simulation, where we use one well-controlled system to basically study the physics of some other analogous system. And here we're mostly interested in looking at the physics of, say, electrons moving in some solid crystals, which are important for a lot of real applications, whether it be just conduction in metals or superconductors or magnetic materials. And the platform that we're using to study this physics is with atoms, basically cold neutral atoms moving in a crystal made of light, so an optical lattice. And one of the key things is that this system is much purer than the condensed matter counterpart. There's not, basically there's no disorder which is inherent to the building of the material, but every sample we make is highly reproducible, and it's a very dilute system where the spacing here is a factor of about 100 or a few hundred times the spacing between centers of the lattice in solid state materials. So even though it's very largely spread out, it's still a very small spacing by normal optical wavelength standards of about a few hundred nanometers between the lattice sites, and we have about 1 million atoms. So it's hard to see directly, say, the entire system. This is a picture of one of our samples in trap, and you can't really see the fine structure. And so we're going to introduce a technique where, kind of in analogy to the scattering of X-rays, we look at the scattering of cold matter waves to detect structure in our system. And so some background, which is maybe not necessary with this audience, but I'll discuss a little bit about matter waves and Bose-Einstein condensates. So we're all familiar with waves in nature, whether it be throwing a rock into a lake and seeing ripples spread out, or standing mechanical waves, where if you drive a string that happens to be tied against a tree. And we can also say accelerate a charged particle back and forth. And this, in fact, leads to electromagnetic waves, examples being, say, X-rays, visible light, microwaves, and radio waves. And usually we're used to thinking of, say, light as a wave phenomenon. And this is pretty well exemplified by kind of a classical Young's double slit experiment, where in the far field, we have light which passes through 2 slits, and the far field interference pattern leads to basically this striped pattern, where you get constructive and destructive interference due to the different pathways that light can take. However, light can also act as particles in some contexts, and this can be seen or exemplified by the photoelectric effect, where it takes photons beyond some critical frequency to actually emit electrons from a surface. And that has to do with the fact that the light is absorbed in quantized amounts, which are called photons. And this leads to basically a wave-particle duality, where depending on the context, one can think of light as either a wave or a particle. And similar such duality exists for massive particles. And it was first proposed in 1924 by Louis de Broglie that particles with mass m traveling at a velocity v can be described by a de Broglie wavelength, where h is Planck's constant in this case. And so we see that for very large m, the objects are described by a short wavelength, and they behave much like classical particles, such as for a baseball. And as you go to smaller mass, they get longer de Broglie wavelengths, and quantum effects or wave effects can come into play. And this is often the case for, say, atomic scale particles, such as the electron or proton or neutron. And in fact, just a few years after this equivalence for massive particles was first proposed, it was detected in the diffraction pattern of electrons from crystalline materials by Davison and Germer in 1927. And since then, it's also become a standard use with neutron diffraction. And both these things have actually become pretty standard tools for characterizing structure in solid materials and in organic materials. And so now let's revisit this equation again, not looking at the disparate masses of the particles, but looking at the velocity dependence. And basically for an ideal gas, one can relate the temperature of a gas in equilibrium to the average kinetic energy per particle by what's known as the equipartition theorem. And you can arrive at basically a scaling of this de Broglie, thermal de Broglie wavelength with temperature. And we see that the lower the temperature, the larger this wavelength becomes. And for most real systems, the wave properties are completely hidden at normal room temperatures. And so what we have to do is cool the particles down. And here we look at a group of, basically a gas of atoms. And at high temperature, they look much like little balls, and they act ballistically. And as we cool them down, we see that the de Broglie wavelengths begin to grow. And at a certain temperature, they will overlap. And this basically fulfills some phase space density argument, where the mean interparticle spacing becomes less than the de Broglie coherence length. And for bosons, this leads to the phenomenon known as Bose-Einstein condensation, and that's where you basically get indistinguishable, large group of indistinguishable particles which are overlapped, and they can be described by some macroscopic wave function. And so how cold do we actually have to be to see this in the lab? So at typical densities, if we just cooled the system down, we would actually, it would be unstable to formation of molecules, and we would create solids as well. So we have to work at very low densities, and in these systems, we have to work also at very low temperatures of about 100 nanokelvin. And then we get gases of atoms which are metastable on the timescale of seconds to hundreds of seconds. And just to put this in perspective, if we represent basically room temperature as the distance from New York to Los Angeles, the temperature scales that we work at would be just half an inch on this scale. So now let's dive into what the experimental system looks like. So as I said, we work with atoms, and so we have our choice of many different types of atoms, and to make things simple, we work with alkali atoms, which have just a single electron in their outer shell. And so they look very much like hydrogen, have a simple energy level structure. And for our system, we use rubidium, which has some very nice properties that make it easy to work with. And how do we cool the atom's motion? So we use laser light, and if we have a simple description of the energy levels of the electrons, we have some ground orbital of the electron around the nucleus and some excited level. And if we tune some resonant laser light, we can excite the electron to some excited state. And the atom as a whole also gets a recoil kick because it absorbs one photon momentum of light. And by the same kind of mechanism of having the atom just absorb photon momentum, we can actually slow the atoms with laser light. And to do this, you can do this in an optical molasses, where you send in 6 counterpropagating laser beams from all directions to create some viscous region at the center. However, what I've kind of smoothed over is that between each photon absorption, the atom has to emit a photon to go back into the ground state. And in emitting this photon, it also gets a recoil kick. And this leads basically to a limit to the accessible temperatures just based on laser cooling, which are not commensurate with reaching Bose-Einstein condensation in our system. So we do have to find some other cooling techniques in the end. So here's a look at the laser cooling part of our laboratory setup, where the atoms are also trapped in what's called a magneto-optical trap. And if we watch a movie of loading a gas of atoms from a background vapor, you see this bright white ball appear, and that's a cloud of about 1 billion atoms fluorescing from all the incident laser light.
That's in your trap, or the video taken by
Oh, this is a video taken by Dominic, I believe, some years ago. So this is our trap.
Oh, okay, the credit for Hal is for laser.
Oh, the credit for Hal is for laser cooling in general. And here's a zoomed out look at the apparatus. So there's a lot of mirrors and different optical elements all over, each of which serve some important role in the experiment. And this is the region of the lab that we do this laser cooling. And so then we have to eventually do an additional type of cooling called evaporative cooling. And for this, we actually have to move the atoms to a much lower pressure chamber. And to do this, we first load the atoms into a very deep magnetic trap by ramping up some current in these anti-Helmholtz coils. And we can see how the atoms respond. Basically, you start from some large cloud, and it gets much smaller because the trap is much stiffer in the end. And then once we have a very tight trap, we can move the coils and the atoms will follow. So this is a video just of moving from the high pressure chamber to the low pressure chamber where we do our evaporation. And the whole setup basically moves on a pair of translating stages. And at this point, like I said, we do evaporative cooling, which is basically the mechanism by which if you set a cup of coffee on a table, it will cool as the hotter atoms and molecules evaporate off. We do the same with the atoms. We remove the hotter atoms and let the whole sample cool. And this is a picture after we drop the cloud. And so atoms at the outer edges are the hottest ones. And we can look at the cloud as we cool. And we see that it gets smaller, and then eventually a high density region appears in the center. These are atoms that are actually in the ground state of the trapping potential. And you get a macroscopic population of about 100,000 atoms in the end in what's a BEC. And how we make these images is we shine in laser light, which creates a shadow behind the atoms. And then we just image that shadow onto a camera using some focusing lenses. And before we image, we drop the atoms and image in time of flight. And so here, you'll see a video of atoms falling, and the whole cloud falls like a rock. And you also see that some features are spreading out as they fall, and these are different velocity components of the cloud. And so essentially, as we drop the atoms, we're going from real space image to a velocity or momentum space image. Okay, and now moving on to kind of the final part of the talk is an experiment on using matter waves to probe structure in an atomic crystal. And okay, so let's consider how we actually detect order in a crystal. And if we consider these pictures of electron diffraction, let's say we have some crystal where the scattering centers are spaced at a distance d. And now we're going to send in matter waves with some velocity v and some wavelength lambda. And much like in the case of electron diffraction from a crystal, we get these Bragg conditions that are fulfilled when basically the distance or the wavelength corresponds to a multiple of wavelength corresponds to the distance between different scattering centers. Whereas there's an angular dependence in the 2D case. In 1D, we just have this simple condition. And so we send in the atoms, and if they match the Bragg condition, they reflect back. And one main motivation for using matter waves in our experiment, as opposed to sending in laser beams to detect structures, that they have a highly tunable wavelength just by changing their velocity. Whereas if you buy some laser from a store, it'll have a very fixed wavelength. Okay, so like I said, we're looking at 1D crystals, but we start from a 3D gas of atoms in a trap. And we create 1D systems as follows. First, we add an optical lattice, where an optical lattice is made from an optical standing wave, which is what you get when you shine in a laser onto a mirror. It reflects back onto itself, and you get a standing wave interference pattern. And depending on the wavelength of the laser light and the energy of an excitation transition in the atoms can either be attracted to the light maxima or repulsed from it. And here we use attractive lattices. And so if we shine in laser beams, we basically split our sample into a bunch of different 2D samples, which are completely disconnected from each other on the timescales of the experiment. And we call this an array of pancakes. And then we can add another set of lasers along the other direction to split this sample up further into a set of tubes, where all the motion of the atoms is then confined to a single dimension along the tube. And within each of these tubes, we can form a crystal by adding a third lattice, which serves to break up the density and restricts the atoms to basically sitting on different sites of the lattice, where we can tune the height of the lattice, and this will control basically the hopping rate of atoms from site to site, and it can also control the interaction strength that atoms feel with one another on a site by controlling their density. And This lattice height, which controls U and J, basically determines the state of the system. So for a large ratio of these two parameters, the system can be described as a superfluid, where the atoms are actually delocalized over the whole sample. And in the opposite limit, the atoms become very well localized in individual sites. This is called a Mott insulator. And for uniform density, this is essentially a perfect crystal where you have the same number of atoms per site. And in the experiment, we'll actually be using two different types of atoms. One which realizes this Mott insulator in certain regimes. And to probe that, we'll be using basically a perfect superfluid which has no lattice along it. And to realize these two states, we're using different hyperfine states of the atoms, where the hyperfine structure comes because of coupling between the nuclear spin and the angular momentum of the electrons, for the physicists in the audience. And so I said we had a very tunable de Broglie wavelength. And how do we actually tune that in experiment? We can do that in one of two ways. So we can either move the crystal into our probe, or we can move the probe into the crystal, analogous to most diffraction experiments. But it's essentially the same either way. It's the same as if I drove into a wall at 60 miles per hour, or a wall ran into my car at 60 miles per hour. My car would look the same afterwards either way. So to get a very well-defined velocity, we actually move the crystal into a stationary probe. So we load these crystal atoms into a deep lattice with two laser beams, and then we quickly frequency detune the two beams to create what's called a moving optical lattice. And the atoms follow this moving lattice for some set amount of time, at which point the two species overlap and they interact. And the other method will be to accelerate the probe in a trapping potential. And for that, we basically set the probe atoms at some height up a potential hill, and then we let them fall to the bottom, at which point they have some kinetic energy or some velocity. And we set this velocity basically just by moving the atoms to different heights up the potential hill. And so a natural natural way to look for structure in the system is to basically do a wavelength scan, where we use a fixed crystal structure and we just vary the relative velocity between the probe and the target. And so at a certain velocity, we see these time of flight patterns where this peak here corresponds to atoms which have been reflected out of our probe. And in fact, these correspond to atoms which have entered the crystal and then been Bragg reflected. And if we scan over this one direction, where this is basically Z, the direction of interest, we see a bright spot of outcoupled atoms. And if we look at now the wavelength dependence, we see a whole line of outcoupled atoms, where we can now count up the population along this line. And indeed, we see three distinct peaks corresponding to first, second, and third order Bragg reflexes of the crystal. And these sit upon basically a slowly varying background, which corresponds to specular reflection from the interface. And additionally, we can also now melt the crystal by tuning this lattice depth S, going from the case of a very deep crystal to the case where there is no crystal at all. And we can examine how the amount of diffraction varies with this change. And as we lower the lattice depth, we see that starting from the case of much diffraction, it basically vanishes completely. And this actually relates quite directly to so-called Debye-Waller factor from condensed matter physics, or what you can consider kind of a Fraunhofer envelope function from optics, where we're varying the size of the different scattering centers, and this determines what kind of allowed momentum change we can have in the probe. Now we can ask what's going on in this extreme limit where there is no crystal at all, but it's just two colliding superfluids. And here we're really studying just 1D collisions between distinguishable particles. And so we can have one of two occurrences when we have particles colliding in 1D and they behave quantum mechanically. They can either move through each other, and this is a transmission event where they don't interact at all, And we see features like this in time of flight, where we find the probe at the incident velocity when we look in momentum space. Or we can get a reflection in the center of mass frame, where the particles collide and they exchange momentum just like billiard balls. And for quantum particles, where we get both of these events, this is what's known as quantum Newton's cradle, where Newton's cradle is just this device shown here, where you can pull a bead back and then it exchanges momentum with other beads on the system. And finally, we can also hope to probe more complicated structure. And here we've formed a checkerboard crystal, where earlier we were looking at matter waves scattering from a normal crystal, where the lattice sites are spaced at half the wavelength. Here we're actually creating a checkerboard with two different types of atoms, one which is attracted to the intensity maxima, another which is repulsed from the intensity maxima, and now their different centers sit at just a quarter of the wavelength. And moreover, we can tune the amount of each of these, the population of each of these atoms, and thereby tune somewhat of an effective polarization of the crystal. And we expect that for this new crystal spacing, because it's at a higher spatial frequency, the Bragg reflex at one recoil velocity should completely disappear. And what do we actually see if we move the crystal at one recoil velocity? This is for the case of a spin polarized crystal of all red atoms. We see a large amount of Bragg reflected atoms. This is for an entirely blue crystal. We also see a large amount of reflected atoms. And then finally, for the mixed case, we see much less. And indeed, we see a distinct minimum as a function of this population imbalance. Okay, so to conclude, hopefully I've shown that ultra-cold gases are a good system to study physics of other analogous systems, such as in solid-state materials. And I wasn't able to talk about some other experiments today, but we've also looked at analogies to quantum optic systems and nonlinear dynamical systems. And so we basically introduced a neutral atom diffraction as a new diagnostic technique for probing structure in ultra-cold gases. Okay, and here's the team of students and PI who have contributed to this research. All right, thanks.